All right, in this recording, we will be looking at population growth and regulation. We'll be looking at different ways of studying whether or not populations are growing or shrinking. So what we'll first talk about is something called a life table and things that are developed from life tables like survivorship curves. And then we'll end by talking about two different measures of growth, one called lambda and one called R. And we'll talk about these in much more detail in class, and we'll actually do some modeling on growth and look at the equations related to lambda and R in more detail. So if you don't quite understand it at the end of this video, we'll go into it more in class. Okay, so how do we know if a population is growing or shrinking? So if there's more individuals in it than there used to be, or if there are less individuals than there used to be, and how it's changing. And also, how do we know, when might be a vulnerable time in an individual's lifetime, and when might they be more or less likely to die, reproduce, or other things go on? Well, there's several different ways we can do this. One way is that we can follow a group of individuals throughout their entire life, and this gets us a whole bunch of information and ensures that our information is very valid because we are studying the same individuals throughout their entire life, from birth to death. This is what we call a cohort. So a cohort would be individuals of around the same age that grow and survive at similar rates. They're growing throughout their life, and we're measuring them every so often throughout their entire life. So by following a cohort and recording data on, are they alive? Did they die? Are they reproducing? Are they not reproducing? We can develop what's called a cohort life table. So a cohort life table is one of the life tables that we'll talk about in this section. Life tables are just tables of data that describe the life of a particular organism. Now, cohort life tables are really mostly used for what are called sessile organisms. These are organisms that don't move around a whole lot. Now, they can be done, and they have been done for mobile organisms, and I'll show you an example of birds that have been used with cohort life tables. But they're really easier to do with organisms that don't move, because it's very hard to ensure that you're seeing all the individuals from that cohort every time you go and look at them. So if you look at this table here, there's a bunch of information that are listed on it. On the left column is age, and you'll notice they don't necessarily go yearly. In this case, it's 3 months. So the first data point was at birth. The second one is at 3 months, and then at 6, then 9, and then 12, and so on and so forth. They also recorded the number of individuals that were alive at each time point, and that allowed them to calculate what percentage survived, and then they can also calculate fecundity. So for instance, at birth, there were 843. Of those 843, 85.6% survived the first 3 months. Now, because it was birth, they were all there at birth, and none of them reproduced within that time period. At age 3 months, there were only 722 left. There was a 73% chance of them surviving to the next time point, and 85.6 survived to be 3 months old. And the fecundity rate is 300 here. This is the number of offspring born to a female while she's at that age. So within that 3-month period, females tended to have about 300 offspring. So this is for a grass, so that's why the numbers are so high. So the big downside to this is that you have to do them pretty frequently, but you do it only for a limited time, depending on the organism. So for things like insects and annual plants, where they don't live for very long, you might only do the cohort censuses for a year. You might do them every month or every week. For larger organisms or longer lived organisms like birds and mammals, you might do an annual or biannual census, and you might do it for 10 years or even more. You might do that. So here's an example of a robin life table. So robin, which is this bird here, and they censused them every year and looked at their from year 0, so birth, up through age 7, and they again looked at the number of individuals, the number that died, the percentage that died, the number that survived, and they were able to then develop this table. Now these can be very tedious. You have to be able to find all the individuals in your cohort every year. You really need to keep track of how many died throughout the time frame that you're looking at. And so they can be very difficult to do, especially for long-lived organisms or highly mobile organisms. And just imagine this life table took someone 7 years to develop, so they weren't able to analyze their data until 7 years later. So what other options do we have? Well, the other method is what's called a static life table. And this is where we don't actually look at individuals over time. What we do is we look at a snapshot of all the individuals in a population at one point in time. And this is what we do most often for humans, because humans live for a very long time. Some humans will live for 100 years or more. And so a cohort life table would take us an incredibly long period of time to get any data, and it might not be as very useful, because the questions that we want answered, we can't answer for 70, 80, 90, 100 years. So a static life table is just a snapshot of time. So here's one of US females done in 2005, and they looked at age classes. They actually looked at 0, 1, 5, and then every 5 years up to age 100. And they looked at, by doing a whole bunch of calculations and estimations, they could calculate what is the likelihood of you surviving, what is the likelihood of you reproducing, and how many years of life do you on average expect to have left. So females that were 15 in 2005 had a 99.1% chance of living 5 more years, so living to the next age class. They, on average, had 0.004 children, so not very many kids at age 15, but there were some. And they could expect to live about 65.6 years. Females that were 30, on the other hand, had a slightly lower chance of surviving, though still pretty high. They had a much higher chance of reproducing, and they could only expect to live for another, 51 years or so. As you go higher, once you reach age maybe 80, you only had a 60% chance of surviving to be 85. You were not likely to be reproducing, and you had on average about 9 years of life remaining. So you can develop all these data points. Now, you had to make a whole bunch of assumptions to develop that static life table. One is that you're assuming that there are about an equal number of individuals born each year. So when you count that there are 10,000 individuals that are age 10 and 9,500 at age 15, that there were 500 individuals that died, when in fact there may have just been fewer born in that year. So you have to look at birth rates, historical birth rates, to really calibrate your static life table and make sure that you're not jumping to conclusions that are not really valid. And there's also some methodological difficulties in doing this, because you might not always know how to age individuals. So it's pretty straightforward in humans. You can ask them, you can look at birth certificate records, things like that. But how do you age a fish? Now, there are methods of doing that, but often they involve killing the fish, so it could be very difficult. And there's some organisms that we really have no valid way of telling their age. So we might only be able to estimate their age to within a certain number of years, and that's not so useful when doing a static life table. Okay, so we can develop information based on a cohort. We can develop information based on static life tables. What do we do with that information once we've developed it? Well, one thing that we do is we develop something called a survivorship curve. And a survivorship curve is just basically plotting how many are alive versus what year is it, or how long have they been alive. What point in time are they over their lifespan? And what this does is it gives us a really good indication of what points in time in a species' life are they more vulnerable. So when are they more likely to die? Are they more likely to die early on in life? Are they more likely to die later on in life? Is there an equal rate of death throughout their life? And basically we can plot this and tell it pretty quickly. So It gives us this nice graphical representation. And survivorship curves tend to fall into one of three different categories, and I would like you to know the difference between these three categories. So a type 1 survivorship curve, shown here for this sheep, but also something that humans have, is one where you have pretty low chances of dying early on in life. It isn't until you reach close to the maximum lifespan of your species that the death rate increases. So you get this curve where it starts out very high number of survivors for a number of time points, and then it drops off steeply at the end. So we're more vulnerable later in life than we are earlier in life. A type 2 curve, as shown here, which is very common in birds, you actually have a pretty equal chance of dying throughout your life. So you're not more vulnerable late in life, you're also not more vulnerable early in life. You are pretty much equally vulnerable throughout your entire life. So this would be a type 2 survivorship curve. And then the third curve, or type 3 curve, is basically the opposite of a type 1 curve, where you have very high death rates early on in life and fairly low death rates later on in life. So you get this big drop off early on in life, but if you make it past the first few time points, then you have a pretty high chance of surviving later on in life. Now these are often species that produce a lot of offspring. They're ones that we talked about in our life history chapter as the live fast, die young ones. They tend to produce a lot of offspring very fast because they don't have long to survive often. So putting them all together, here's the three curves. So type 1 again, most individuals die late in life. Type 2, individuals die at a fairly uniform rate. And type 3, most die fairly young, but the few that survive past that initial point will tend to live longer lives. Now in class we will talk about these three classes in a little more detail. We'll also look at how these different survivorship curves might vary even within a species. So you might not get it uniform survivorship curves across species, populations and species, and we'll look at why that might be a little bit more detail in class. Okay, the final thing for this video that I want to go into is how can we use the data from a life table to project whether or not a population is going to get larger over time or whether a population is going to shrink over time. So what we end up having to do is looking at how many individuals there are within a given age range, how many of them are female, and then for each of those females, how many of those females are likely to be having children. So we developed what's called the age-specific fertility rate. And so how we do it, here's an example of this. So let's say we had 100 females at a certain age, and from those 100 females, there were 75 female offspring. Now we only look at females. One, it simplifies things, but also females are the ones that are reproducing, and so females are the important ones when considering whether a population is growing or shrinking. One male, for instance, could be the parent of multiple children for multiple females, so it simplifies things to just look at female offspring. So if 100 females produce 75 female offspring, then we have a fertility rate from that age range of 0.75. So the average female will produce 0.75 offspring in that age group. So females of that age produce 75 or 0.75 female offspring in that year. So what we can do is for every age class estimate age-specific fertility from our life table data. So here's one from a beaver study that was done in 1984. They started off with 3,695 beavers. They followed them for 14 years, and for every year they calculated the age-specific fertility. So you'll notice that in year 1, there was on average 0.315 female offspring per female. So of those females that were alive at age 1, they produced on average 0.315 female offspring. At age 10, the females that were alive at that point were much more likely to have offspring. They had on average 1.8 offspring per female. Now you might think that, okay, they produce a lot of offspring later on in life, but what you have to notice is that there are many more females that are alive at age 1 and very few females that are alive at age 10. So although the females alive at age 10 produce more offspring per female, there are so many more females alive at age 1 that more offspring are produced by young females than are produced by old females. Okay. So what we can then do is combine those two numbers to find, what is the average number of offspring per age class rather than the average number of offspring per female. And we notice that at this point the average number of offspring per age class is lower in year 10 than it is in year 1. But this gives us an idea of the total number of offspring produced through the whole population. And if we add up all these numbers, we can then estimate the total number of offspring born to all females of all ages. So essentially, if you were a female beaver, what is the likelihood that you're going to have a child, and how many children on average are you going to have? And when we add up all these numbers, we get something called the net reproductive rate, or lambda. So adding them all up here, we get a lambda of 0.938. So what does this mean? Well, this means that per female throughout the course of her entire life, whether she lives 1 year, whether she lives 10 years, whether she lives somewhere in between or somewhere longer, she is going to, on average, produce 0.938 female offspring. So each female produces 0.938 female offspring per throughout her entire life. So what does this mean? Well, 0.938 female offspring per female means that she's not replacing herself. She's on average having fewer offspring than one. So not every female is going to reproduce throughout their life. So what does that mean? Well, because lambda is lower than 1, this population is declining. Okay? If lambda was equal to 1, the population would be at equilibrium. That means on average each female has 1 female offspring. She's replacing herself. But if lambda had been above 1, that would mean that the population was growing. Right? So she's having more female offspring than 1. That means that she is producing more than enough to replace herself. So the population will grow over time. Now, thinking about how we went about calculating lambda, well, we had to first have a life table that told us not only how many individuals there are, how many female individuals there are, how many female offspring they each had every year. We then had to do a bunch of calculations where we looked at how many offspring does she have in that age class, how many offspring are had per age class, and then we had to add them all up. And this can be very difficult to do because we might not have all that data. So a much easier method to look at, rather than looking at lambda, is to simply look at how many births there are in a particular year or a particular month, and how many deaths there were in that particular period of time. And this might be something that's much easier to do if you're following a population. So how many were born and how many were dead. This can lead you to a very simple calculation. So if the number of births minus the number of deaths is greater than 0, that means there were more born than died. If the number is less than 0, then there were more that died than were born. So this birth minus death formula, we usually simplify to the letter R, and this is what's called the per capita rate of increase. So per capita, were there more births or more deaths? So we often take birth minus deaths divided by total number of individuals, and that's where it gets the per capita. Again, we'll talk about this in more detail in class, and this doesn't make sense here. Okay, so very similar to lambda, R gives you an idea of whether a population is growing or not. In this case, the break-even point is 0. So if there are no more births than deaths, but the exact same number, then you've replaced the losses. So for every individual that died, you had one that was born, the population is not going to grow. If there are more deaths than births, R is going to be less than 0, and the population will decline because more died than were born. If there are more births and deaths, then R will be greater than 0, and the population will increase. Now, they're very similar, though they are looking at different things. Lambda looks at generational growth rate. R is an instantaneous rate, can be calculated at any time. R is often more used, and so we will tend to stick to R when we were talking about growth and looking at models of interactions between species later on in this course. Okay?